Welcome to the fourth episode in a series for calculating pi on my relay computer. Here's the journey so far. And it started with a challenge. A gauntlet laid down. Simple enough, calculate pi. But this is referring to my relay computer. And this thing is pretty limited. An electromechanical 8-bit computer with the most basic of functions. Which means calculating pi, let alone to 20 decimals, well, it's not going to be a quick or easy task. But then, where'd be the fun in that if it was easy, eh? And so here's our goal, the precision of pi that my computer needs to calculate. How so? Well, there's many ways to calculate pi, but I've settled on a binary-friendly infinite series, the Bailey-Borwein Plouffe formula, or BBP for short. Tiny issue though, the BBP formula produces a result in base 16, and so it would be pi in hexadecimal that my computer produces, and not decimal. That's not insurmountable though, and we already know how to convert between binary and decimal, and so in the last episode, we took the BBP formula and broke it down into high-level pseudocode, and then onwards into modern .NET code to prove things out and better understand how the formula behaves over time. By the end of the episode, we ended up with two things on the to-do list. First, our pseudocode has many variables, and so we'll need to think about how and where to store them. Secondly, we'll need to build a shopping list of the operations we need to implement, and then that's where the real work starts. If we're lucky, the items on the shopping list might be something the relay computer can do natively, but it's far more likely to be something we'll just have to piece together. Righto, let's get cracking. And we'll start with the variables, and to help out, let's bring up some of the intermediate results from last episode's .NET code. Here we've got the second and last iteration at k equals 1 and k equals 16. Our first variable then is sum, which holds the value of pi building up in each iteration. From the .NET code, we know the number of bits required to hold the sum, but something we'll need to consider for the relay computer is our byte boundaries. Everything the computer can do is byte by byte, so we need to align with that. Now there's options here, and it might be tempting to keep the integral part in its own byte, but again, these are all ones and zeros to the computer, and the fixed binary concept is completely of our own making. I think therefore it makes sense to split the value like so, and hold the sum across 10 bytes. Another way of looking at this is that each byte is holding 2 hex digits of pi, beginning with 32, then 43, and so on. Now this choice may cause headaches later for converting to decimal and so on, but for now it's the more optimal place to start, as otherwise dedicating a byte to the integral part means an extra 4 bits on the fractional part. Anyhow, let's get a table going and add our sum variable to it, which will be 10 bytes of fixed point binary, and as such there's only one option for storing it, it'll have to go in memory. Next, let's look at our looping variable k, which we know will always be a positive integer, so that simplifies things somewhat. We can also see here that dv is derived from k, so it's tempting maybe to loop on dv instead and bump its value by 8 every iteration, but we also need 4 times k for the right shift later. Values for k and dv aside, we also need to think here about how to implement the loop itself. Let's quickly pull up my computer's architecture diagram. And there's 2 8-bit registers attached as inputs to the ALU, and if we load register B, we can then increment that value, or we can load registers B and C and then add those values together, and the result of which we can place in registers A or D. Fair enough, but what's also key here is the 3 condition registers. Z is set for a 0 result, that is, when all bits are 0. CY is set for an arithmetic carry during an add or increment operation, and finally S is set when the most significant bit of a result is set. These condition flags are held until the next ALU operation, and having these available means we can make branching decisions and, in the case of our pseudocode, decide when it's time to leave that loop. A typical approach here is to start the loop with a negative number via 2's complement. So in our case, we start with minus 17 and then increment by 1 at each iteration and branch out if the 0 flag is set. That approach though does mean k needs to be independent of the other values and focus solely on counting the loop. There's other choices too, like storing 16 somewhere and then after each increment compare k using a bitwise exclusive OR and then branch if the result was 0. Choices. I think for now though I'll go with a separate k approach. But we can always optimise the program later on, and even small changes can have a big time impact, even more so when you're doing loops. Note that I've put down register storage is the ideal here, because moving things between memory and registers adds yet more runtime and complexity. The challenge to that ideal is we only have a limited number of registers to play with. In fact, juggling registers is pretty much a full-time concern when programming my relay computer. Right, so given we're keeping k separate, we need to find a home for the dv variable here. Well, we know it maxes out at 8 times k, so 128, and that'll comfortably fit within 8 bits, so it's another candidate for register storage. Ooh, and actually, ending on 128 does open opportunities to maybe combine k and dv after all. See, it takes 7 bits to hold a number up to 127, so on the last iteration, when dv ticks over to 128, that addition would also set the sign flag. And that approach works best if rather than setting dv to 8 times k here, we instead increase dv by 8 each time at the end here. And that way it's ready for the next iteration. Anyway, one to keep an eye on. Moving on, the values a, b, c and d we already know will be the same variable type as the sum. Then finally, v and vs are likewise. Although what's quite interesting here is that right shifting v into vs means we increasingly throw bits away at the right hand side. So there's potentially optimizations we could make by decreasing the variable sizes over the course of the program. For example, looking at the outputs for k at 16, we see we're only impacting byte 0 of the sum, and therefore we could calculate a, b, c and d to a lower precision, provided we get the same result of vs when right shifted. Again, something for us to consider come programming time. Speaking of which, let's take a look at the operations we'll need and build up our shopping list. So this time let's work from the sum variable backwards. Sum is 10 bytes, and at each iteration it will need vs adding to it. My relay computer can certainly do addition, but only with 8-bit values. Here then we'll need to perform byte-by-byte long addition. Variable vs here comes from v right shifted 4k times, and we know that v will also be 10 bytes, or maybe less if we make that optimization. Now unfortunately my computer doesn't have a right shift, even an 8-bit one, so we'll have to get creative, but either way it doesn't change our need for a long right shift. Next we've got some long subtraction, or maybe we haven't. My relay computer doesn't do subtraction. No, it's not been a diva. There's just no need, because if you add a negative number the outcome is the same. Most likely we'd approach this via a long 2's complement to make variables b, c and d negative before adding them to a to get our intermediate result v. I'll put it on the list for now as long subtraction though. Actually thinking about it, it might be even easier to calculate b, c and d using -2, -1 and -1 rather than 2, 1 and 1. That sounds enough in decimal mathematics. -2 divided by 4 is -0.5, which is what we'd want, but I'll have to double check it doesn't trash the binary division routine. And speaking of which, that's the meaty one. Divisions are by far the most complicated operation in my view, and we'll probably need a whole episode to explain and implement. In fact, I've only a vague idea of how to do it right now, but that's one for me to fathom out and one for you to enjoy in a later episode. For now though, let's note it down on the shopping list as it's core to our calculation. With all the long items taken care of, we're just left with basic 8-bit additions and increments. This will be used in our loop counter k, the dv value and for the 4k at the right shift. Note that I'm avoiding multiplication here because of the k loop. We can just use simple repeated addition instead. Okay, I think that's it. There'll no doubt be things discovered as we get deeper into coding, but right now that's what the pseudocode is telling me I need. Right, let's see if there's anything we can tick off the list then. Well, the add increment is pretty straightforward and my relay computer has that natively, so that one's done. Which leaves us with the 4 long operations. Each of these will have similar challenges with moving bytes in and out of memory, so let's start by taking a look at long addition, which is arguably the easier of the 4. And let's start with a quick example, a reminder of 8-bit binary addition. Here we're adding the first 2 rows to get the third row, and just like with decimal addition, we go right to left, adding up each column and carrying where needed. In the block highlighted we see the basic outcomes. 0 and 0 is 0, 0 add 1 is 1, and 1 add 0 is 1. Nice and simple. When we add 1 to 1, the result is 2, or 1 0 in binary, and so we place a 0 in our result and carry the 1. With our carry, the next column is 1 add 1, add the carried 1, which totals 3. So 1 in this column and 1 carried to the next column. Super, let's look at the last bit. Here we have 1 plus 0, which is 1, and therefore there's nothing to carry. The byte we've summed so far won't change now, and we can stash it somewhere in memory. Having nothing to carry means there's nothing special for the next byte, and we can just approach it just as we did for the first byte. Addition works just as before, but let's focus on the last bit again. And here, 1 add 1 is 1 0, so we do have a carry this time. In this case now, there's additional work to do, and after we've stored the current result byte, we have to get the carrier bit over into the next byte. There's a couple of ways of approaching this. We could increment one of the input bytes before adding, or increment the result byte before or after adding. Either way, it's something we have to handle ourselves, as my ALU doesn't have a carry-in ability. With our carry bit brought in though, we get the correct result of 1 1. And from there, the addition continues as normal. At the end of the third byte here, our 1 add 1 causes a carry, and then that has 1 added to it, so our result here is 1 0 0, with the 1 carried on to the next byte. If this is our last byte, then the result needs to be 1 byte bigger, and that byte will have a value of 1 coming directly from the carried bit. OK, long addition doesn't sound too bad then, but how does that work in practice, and how do we juggle those bytes in and out of memory? So let's take a look at an 8-byte long addition. And to keep things compact, I'm using hexadecimal now, with each pair of digits making up a single byte of the overall 8-byte value. As before, we want to add the first and second rows together to get a result in the third row. Before we go any further, let's pull in the architecture diagram again, as we're certainly going to be needing it. My relay computer has 8 general purpose registers: A, B, C, D, M1, M2, X and Y. And with each only holding a single byte, this is why the computer has memory. Quite a lot of it in fact, and with a 16-bit address bus we can store up to 65,536 individual 8-bit values. For our example here though, 24 slots will be ample. Here our first row is stored in memory addresses 0 through to 7. The second row goes in addresses 10 through to 17, and finally we reserve 20 through 27 for the result. Note here that the result boxes are shown empty, but in reality because of how the memory chip works they could contain any random value, and we must never assume the state of any memory that we didn't set ourselves. Our first job for long addition then is to add the least significant bytes together. Well, the ALU is where we do arithmetic, and that means we need our bytes placed in registers B and C so that the ALU can get at them. How do we do that? Well, we know the destination, where to put them, but we also need to tell the computer where to get them from, the source address. This is where M1 and M2 combine into the 16-bit M register. M1 forms the high byte and M2 the low byte, and so if we set M1 to 0 and M2 to 7 like so, we're now addressing location 7 in memory, and we can copy the contained value via the 8-bit data bus into register A, B, C or D. Let's take the 35 in memory over to register B. Similarly, we can load register C with a value of 92 after setting M to point at address 17 like so. Perfect, we're all set up for our first addition, so let's get that done and place a result in register A, which gives us a hex result of C7. As you'd expect, hex follows the same addition rules, so even though the relay computer does it in binary, we can say that 2 add 5 is 7, and then with no carry, 9 add 3 is 12, or C in hexadecimal. There was no carry from the overall addition, so we're fine to store this result back in memory and move on. Cool, that's our first byte calculated, and we can go on to the next byte. Well, actually, hold on, there's something I've completely glossed over. Any guesses? How do I know where in memory to find and place our values? So far I've just been setting the M register directly via some sort of magic, but magic ain't going to cut it in real life. We need some way of storing where the values are. So what do we need? Well, for our addition just now, we addressed 3 separate locations: 7, 17 and 27. So with 3 16-bit addresses, we'd need 6 bytes of information somewhere to hand. Now, it just so happens these addresses have a high byte in common, 0. Maybe there's some sort of trick we can pull. And indeed, one approach is to think of the high byte as referring to 256 unique pages of memory, with each page having 256 locations defined by the low byte. Thinking that way, all three addresses are in the same 0 page, and so we only need to track the low bytes of 7, 17 and 27. And that also means we only update the M2 register each time M1 stays as 0, referring to the 0 page. So 3 bytes then, but where to put them? Well, there's 3 registers free, D, X and Y, so maybe we're in luck. But actually we'll likely want D for tracking loops and swapping register values around, and if you're familiar with the Towers of Hanoi game, then you'll know why keeping a register free is a good idea. What to do then? Well, there's another optimization we could make. After adding each byte, we no longer need the original values. We can overwrite them. With this approach, one of the values effectively becomes an accumulator, and that's really handy when adding multiple values together, just as we'll need to do in the pi calculation. So in this case here, our C7 is placed in memory location 7 instead, like so, and that saved us 8 bytes of memory, and given us 1 less location to track. And with just 2 locations to track, we can now use registers X and Y like so, where X has the low byte of location 7 and Y has a low byte of location 17. Each time we need to refer to one or the other, we copy X or Y to M2 and we're good to go. Perfect, we can move on, except how do we move on? We need to update X and Y to point here and here. But address 6 and 16 are 1 less than X and Y currently hold. We'd need to decrement X and Y. So we could copy X to register B and set C to -1 and then add the two together, which would result in this. We'd then copy the 6 in register A back to X and M2 and we'd be all set up. That all feels a bit, let's say, cack-handed though. My computer is geared up for incrementing, not decrementing, and the ALU can directly increment a value in register B, but we also have an extra trick available. Just like the M register, the X and Y registers can also combine into a single 16-bit XY register. So what? Well, we can then use a 16-bit incrementer unit to bump the XY register up by 1. Now in our case here, this only helps us with the Y part, as 0717 becomes 0718. And we'd also need to be careful if Y was FF, as that would then turn 07FF into 0800. But using the 16-bit increment functionality saves us at least 2 operations versus shifting registers around. Interestingly, the XY register is sometimes known as the index register because it's often used to track through locations in memory. Here we're being a bit sneaky though, and using it to store 2 locations in memory, with the only caveat being that they must exist on the same page in memory. Anyhow, all this talk of incrementing registers is lovely, but our values in memory aren't laid out that way, so this all seems completely academic for the problem in front of us. Well, there's one way to fix that, of course. We just store the values in reverse byte order, with the least significant byte first, and then that means our X and Y registers start at 0 and 10 respectively, and can be incremented by 1 each time to move through the bytes. The last thing we need to consider is how to know when we've reached the last byte. And that's where we can use register D to store the address immediately following the last byte of our accumulator, like so. At every increment of X, we compare with register D, and if the values are the same, then we must have gone past the end of the accumulator. Right, let's get this sum going, and we'll run through it until we hit a carry. So we increment XY, and then increment X by copying it to register B, performing an ALU increment to register A, and then copying it back. We can now load register M2 with 11 and pick up our next byte like so. Likewise, we copy X to M2 and pick up our other byte. And we can then perform the addition and store the value like so. And because we loaded register M in this order, we're already pointing to the right location to store the result. The process now repeats like so. And on this calculation step, looking at the B and C registers, we have 4 plus 4, which is 8, and then 4 plus C, which gives us 0, carry 1. So in this case, our carry flag is now set. Straight after storing the result, the code would need to check the carry flag, and if set, move into a carry handling phase. Here, the approach I'll use is to increment M2 to point at the next memory slot, like so, which we can now load into register B, and then increment it into register A like so, and then we place that value back into our current memory location like so. And we're ready for the next iteration. The reason why we perform the carry this way is because if the increment here also produces a carry result, that is, we were incrementing FF, then we need to repeat this operation of moving to the next memory cell and incrementing. And we repeat this process until we no longer get a carry. From here now, we can continue the sum like so. At this point we have another carry, so we would increment the next byte in the accumulator. And we're good to carry out the final addition. And at the next increment of x and y, x now matches a value in the D register, and so we know we're done and can exit the loop. With that done, our long addition is complete, and we could continue adding further 8-byte values to our accumulator value. Cool. Right, let's return to our shopping list. So I think we can confidently tick off long addition now, at least from a theoretical perspective. And although that took some time to go through, it sets us up nicely for the other long operations, which, as mentioned earlier, will also have the same challenges of iterating through memory byte by byte. So we'll be able to reuse a lot of what we've learnt. In terms of next steps though, I think it makes sense to plough further ahead with the long addition first and code it up for the relay computer and actually give it a run for real and turn the theory into reality. Sounds good? I bet it does. One problem. My relay computer isn't Turing complete yet. Beg pardon? Well, let's look at what it can do first. This is the instruction set that's fully implemented in the relay computer. Moving 8-bit values between registers, setting a literal value into register A or B, performing 8-bit ALU operations, moving 16-bit values between registers, and finally branching operations. To be Turing complete, there's two key instruction classes missing: loading registers from memory and storing registers to memory. This is absolutely key to implementing the long addition routine, or, for that matter, anything more than a pretty rudimentary program. While we're at it, there's also another key instruction class that we'll need for the long add, the 16-bit XY increment. There's also one final class missing, the cunningly titled miscellaneous operations. But they're not going to trouble us too much right now. It's the load, store and inc XY operations that we need. And so next episode we'll go full Turing by implementing the missing instructions, and then we can code up and try our long addition routine. And that'll be one hell of a milestone completed for the relay computer. In the meanwhile though, that about wraps it up for this episode. So as always, thank you for watching if you've made it this far, and I'll see you next time.